Okay, let's look at example problem 7.3. We have this diagram. We're supposed to create shear and bending moment diagrams for this thing. Okay, so right off the bat, we know, because we're smart people, we know we're going to end up needing to get these forces here. So how do we do that? Well, I'm going to take my sum of my moments, say at A is equal to 0. So this 40 pounds per inch times 12 inches, I'm going to replace that, do a nice and good color. I'm going to replace that with a single force here of 40 times 12, which is 480. And this is going to be at 6 inches to there. So we have 480 times 6 plus 400. So in this distance from here to all the way over to here is 12 plus 6 plus 4, so times 32 is equal to B, sorry, not 32, that's equal to 22 is equal to B times 32. So therefore, B is equal to, if I'm not mistaken, 365. And when I take my sum of my forces and y equals 0, it's going to tell me that A is equal to 515. Okay, so now I have my two external forces. So let's replace those. I'm going to come in here. So this is equal to 365, and this is 515. Okay. So now let's start talking about this problem. What I need is I need to replace this whole thing, right, with a single beam, and I need this beam to look like this. I need a beam here. I'm going to have a force here of 515, right? I have a distributed load across a section of it, which is 40 pounds per inch. I need to, and the key is here, I'm going to move this force over here. I need to say there's a force here. And so I need to replace this force here with an equivalent force couple system at this point right here. Okay, so what is that? Well, the beauty is you can just move, it's going to be 400. But by moving it this much, I have kind of lost 400 times 4. So I've lost 1,600 inch-pounds. And so I need to add a couple here of 1,600 inch-pounds. And then lastly, we have 365. Okay, so this is what I'm trying to create the shear moment diagram of. So that's what we're going to go for from there. Okay, so now that we have that, let's think through how to do this. So first off, let's draw, we'll just do it right here. This looks like a lovely place for it. Boom. We have the shear, and we have the moment. Okay, so let's just kind of draw down these lines. So obviously we have things going on here, here, and here. Okay, so we just learned that simple loaded, when you just have a single force here, it stays constant between forces for the shear and this linear for the moment. Now we have this distributed load. So let's think of how that works. Okay, so let's come in here and let's look at this section, say right through there. We're purposely going to go into the middle of it, right? So if we draw that, we have a 515. We have some distributed load here. And then we have the V and the M. Okay, so what is this? This is 40 pounds per inch. And let's call this at some X inches. Okay, so what is the shear? Well, if I take my sum of my forces in y equals 0, so I have 515, the up's equal to the down, so that's going to equal 40 pounds per inch times x inches, that's going to be the total pounds, plus v. So v is equal to 515 minus 40x. Okay, so let's kind of think through this. So at x equals 0, the equation is going to tell us that v equals 515. Does that make sense? Well, at x equals 0, we're going to have this beam here. We have 515, so I'm going to make that super short. We have basically no distributed load, right? And we have v and m. Well, if the distributed load is basically 0, v has to be 515. So lovely. So that means that we're starting up here. I'm going to try that 515. Okay, what about at x equals 12? Because this is only valid till x equals 12. So then we're going to have v is equal to 515 minus 40 times 12. So 515, 40 times 12. So that is going to equal 35. Okay, so that means that here at this point, we're going to come down to 35. Okay, and we see the equation of this thing right here, right? So it's a nice straight line. So this is going to be a straight line from here to here. Okay, so let's move just a little bit. Yeah, try that again. So my pen is not quite the same as you'd think it would be. There we go. Lovely. So there's 35. So now what happens between here and here? Well, there's no load, so we know it's going to be constant, right, across there. And then we have this discontinuity. So let's look at that. So we have this beam, boom. We have 515. We have a distributed load, but quite frankly, we're past that point of the distributed load. So I'm going to replace that distributed load with the 40 times 12, which is, I'm going to replace this with just a single force here of 480. And then we go past that point, and we have V and M. So if I take my sum of my moments, or sorry, my sum of my forces in Y equals 0. So we have 515 up is equal to 480 plus 400 plus V. So V is going to jump down to 515, subtract off 400 and 480, and it's minus 365. So this is going to drop down here to 365. And then it's constant all the way across there, and then it comes back up to there. Okay. That is our shear force diagram. Okay, so the shear force is looking good. So I don't know if it's straightforward, but it's not too painful. So now we have to figure out the moments. So I'm running out of space here, so I'm going to clean up some of my space, erase some of this stuff. Let's come over here and look at the moments. Now, we talked about in the previous problem how the area under the curve is the change of the moment. So what is a moment when it starts? Let's look at the very beginning. So boom. Well, I kind of keep drawing that like it's the whole thing is if you just have a little tiny section, you have a force here of 515, you have a real small distributed load, and you have V and M. But if this distance is 0, the distributed load is 0, the V is here. If you take the sum of my moments, it's going to tell you that M is equal to 0, which makes sense, that we're starting here at that point. Now, let's figure out the change to this point. So what is this? It goes from, we can figure out the area, break this into two parts. So the area, we'll call this part 1 and part 2. Actually, look at this, we're going to change colors. Ooh. So the area of 1 is going to be 1/2 base times height, right? 1/2, it's 12 long, and the height is 515 minus 35. So the area of 1 is, so 6, 515, boom, is 2880. 2880. The area of 2 is 35 times 12. So 35 times 12 is 420. So the area is 420 plus 2880, which is 3300. So come back to here, this is going to hit, so right here, we're going to call this 3300. Now we go through and it's not going to be a straight line. It's going to be instead a curve like that. And how do I know that? Well, let's come back over. Let's look at this. So we have a beam, and now we're going to look at some distance, right? We have 515. We have some distributed load of 40 pounds per inch. I have my V, and I have my M. So if I take, and this is now some x distance, okay? So I take my sum of my moments at A is equal to 0. So the 515 goes away. So I have the force that's going to be 40 inch-pounds times x inches. That's going to give me the total thing, and it applies in the middle, right? So where's that middle? It's going to be times x over 2. So that's the moment going in that direction, plus v times x that's going to equal to m. So there we go. So this is 20x squared plus v times x is equal to m. But what is v? Well, it's right here. We figured this out. So this is 20x squared plus 515x minus 40x squared is equal to m. So m is equal to, what is that, minus 20x squared plus 515x. So again, as a gut check at x equals 0, the moment is 0, right? And at x equals 12, because this is only good for during that distributed load. Sorry, sneezing fit. At x equals 12, then what is it? It's going to be 20 times 12 squared. So that's going to be minus and 515 times 12. So that's equal to, the moment is 3,300, which is, lo and behold, what we got right there. So that's all good. So we have this curve through here. Now we can kind of go back to the easy stuff, right? So from here to here, we notice the area under this curve. So the area under that curve is, how far is that? It's 6 inches, and the area of this area is 6 times 35. So what is 6 times 35? It's a 210. So it's going to go up by 210. So when you add that to 30, it's going to go up to 3510. So that's a straight line, right, to 3510. 3510. Okay, and now here's the one thing where you got kind of a weird thing going on. And what is that weird thing that's going on now? Well, quite frankly, you have a discontinuity. Just like, we have all these discontinuities that we deal with over here. Now we have this moment that's just sitting right here. We have this moment. And so on the one side of that thing, you got 3510. On the other side, it's going to go up by 1600. So if I add 1600 to that, it's 5. So it's going to go straight up to 5110. And it's going to go straight up to that point right there. And then it's pretty straightforward, right? So then it's just going to go sloping down to the bottom. So where does this discontinuity come from? Well, let's play with this. So we have this beam, boom. Okay, so we have 515. We have this distributed load, which we're going to replace with a single load of 480 in the middle, right? Because we're past that point. We also, so we're getting to this point where we have V and M. And this is just before, we're going to look at this point right here, right? Just before that force. Okay, so if I take my sum of my moments equals 0 at A, so we have 480, sorry, that's ugly, 480 times 6, right? Is going to go in that direction, plus V times, what is this distance? It's going to be 12 plus 6, so times 18. 18 is equal to the moments. So what is the moment going to be at this point? Well, again, we should know this. It's a 486 times, and then V. What is V? Well, we know what V is. We figured it out. V right here is 35, right? So 35 times 18, add those together, and it's 3510, which we already knew. So now let's look at it just on the other side. So I'm going to tweak it just slightly, right? Now I have this 400-pound force there and a 1,600 inch-pounds, and then I have V and M. Okay, so now we're going to take the sum of moments at A equals 0. So we're going to have the same thing. We're going to have the 480 times 6, right? Because we're dealing with that whole thing. But now we have plus 400 times, what is the distance again? 18? Yeah, times 18. And then we have plus 1,600 plus V times 18 equals M. So what is V at this point? Now remember, we're talking at this point right here. We just came over to this point right here. And what is V? It is minus 365. So if you go through and crank this out, it's 480 times 6, and then 400 times 18, and then plus 1,600. And then now you have V of minus, what do we say, minus 365. So 365 times 18, and add them together, and moment is 5110, which is what we figured out there by adding that discontinuity there. So it works out. So there you go. So that is the shear force, the shear and bending moment diagram for this problem. So the key, again, summary real quick, is we have to take this overall thing. So I'm going to see if I can do a highlighter. We take this overall thing, right? And we want it to turn it into this. Oh, that was super not what I meant to do. Sorry about that. We want it to turn into this right here, right? We need to have a single beam with some forces applied, the distributed load. We have a moment applied even, which is a little bit different, but still it's okay. And then we have forces. And in order to do that, we can walk through and we can find this answer. There you go.